Ladies and gentlemen, good morning and welcome back to Engineering Dynamics. In this video, we will get the equations of motion of a system with two masses, three springs, and a dampener, so a non-conservative force. And we will do that by applying the Lagrange equations. So let's jump right in. Let's look at our system first. We have two masses that are moving along a rod, and that rod has the angle alpha relative to the x-axis. So we have mass 1 right here and mass 2 right there. Attached to mass 1 that is gliding along the rod, we have a spring C1. Then we have a spring between mass 1 and mass 2. And we have the last spring that is attached to the rod at point B. And of course, let's not forget that we have the most important part here, that is our dampener. So we have a non-conservative force. And now we need to follow our recipe that we know. So we get the kinetic energy first, we get the potentials, then we project the non-conservative forces, sum everything up, and this will be our equations of motion. So let's first think about our Q's, so our generalized coordinates. To categorize the system fully, we only need three variables. That's first, the position of mass 1 along the bar, the position of mass 2 along the bar, and the angle alpha to place the bar in space. So that's why we have S1, S2, and alpha. Now we need to find the kinetic energy. Because we chose S1, S2, and alpha, we have a fairly simple expression for the kinetic energy, and that is 1.5 times m of S1 dot squared plus S1 squared times alpha dot squared. So the first part is the velocity of point mass 1 in this direction. But if alpha is changing, we have a tangential velocity in this direction. And because we need both of them, we have this one, this part, and this part. The same is true for mass 2. In this case, we just replace S1 with S2 because we have, again, don't forget the squared here. So we have S2 dot squared plus S2 squared times alpha dot squared. So now we have the kinetic energy. The potential energy is also very simple. We have M1 times gravity times sine alpha S1. And for mass 2, we have mass 2 times gravity sine alpha S2. Also very simple. So now that we have two masses, two potential energies, and two kinetic energies, we go over to the springs. We have three springs, so we will have three potential energies for the springs. Let's get rid of this. So we have 1.5 times C1, that's the constant for spring 1, times S1 minus L1 squared. Don't forget the squared. So L1 is the length of the spring where it's not in compression and not under tension. We do the same thing for spring 2. We have 1.5 times C2. And here we have to consider that if S2 and S1 are both moving in the same direction with the same magnitude, we will not stretch the spring because this will move as a fixed object relative to each other, and we will not apply any tension or compression to the spring. That's why we need S2 minus S1 minus L2, and don't forget the squared. For spring 3, we have 1.5 times C3, and here we have to think about the sinus, the sine, because we have this our length B, so this is our cosine alpha, and this length is our sine alpha. So we have sine alpha times B squared. So now that we have the potential energy and the potential energies and the kinetic energies, we sum everything up and get the total kinetic energy of the system and the total potential energy of the system. Now we have to think about the non-conservative forces. So this is actually the most important part where you can get a lot of things wrong. So we know that we have a dampener. Let's look at the dampener again. Get rid of this. We have a dampener, and the dampener is basically always doing the opposite of what you want to do. So if you're moving away from that direction, the dampener is trying to hold you back. but if you try to move into the direction of the dampener will try to push you away. So if we assume that S2 is moving faster than S1, so S2 is moving in this direction faster than S1 is moving, it will try to pull mass 2 back and push mass M1 in this direction. So this will be our free body diagram, that we have mass 1 here and mass 2 there. So we'll push mass 2 back, or we try to hold it back, and we try to pull mass 1 along with us. So this is our force that is proportionate to d, the constant of the dampener, times the velocity that we're moving. Now we deconstruct the force into cosine and sine. For force 1 on mass 1, we have cosine alpha times F, and sine alpha. For mass 2, we have the same thing, just with different sign at the beginning. So it's not a plus, it's a minus. Then we have to do the projection. We have to get the position of mass 1 where the force is attached to. So it's du1 dq, and multiply it with our force. So then don't forget the transposed. So the position of mass 1, that's where we had the cosine and the sine before. This is right from, we used it here. But if we do it in a full expression, we have cosine alpha and sine alpha S1. So now we have to derive the position of mass 1 with our q's. So we have du1 ds1, du1 ds2, and du1 d alpha. So we get a cosine and sine. We get 0 for S2 because this is not dependent on S2. And then we have a minus sine alpha and a cosine alpha if we derive with alpha. Now we do a transpose. We transpose this whole matrix and we get this matrix vector multiplication. And we see that we simply just get a F0, 0 because cosine squared plus sine squared is 1, and minus cosine sine plus sine cosine is 0. So that's why we have nothing here in the third line. So this is for mass 1. Now we have to do the same thing for mass 2. So we get the position of mass 2, and then we have to do the partial derivatives with our q. So this is du2 ds1, du2 ds2, and du2 d alpha. So we get cosine and sine, and minus sine and cosine. And if we do again our transposition, so this has to be transposed, we transpose that and do a simple matrix vector multiplication. Sorry for that. We get minus 0 f0. We have nothing in the third line because cosine times sine plus minus sine cosine is 0. So this and this will cancel out, and that's why we have again nothing in the third line. And now we have to do just the thing that we did before, that where we derive our potential energies with q dot and take the absolute time differential minus the kinetic energy derived with our q's plus the potential energy derived with our q's. This has to be transposed, of course, and we will get our and this will be equal to our non-conservative forces that are projected, and this is our equations of motion. So we will have 3 equations of motion because we have 3 generalized coordinates. I hope this video gave you a better understanding about the application of the Lagrange equations, and that even if we have multiple non-conservative forces, dampeners, or springs and a lot of masses, it's still better than just applying the principle of virtual work because we have way less calculations to do. And as soon as we have the equations of motion, we can give them to the computer and solve them with some kind of symbolic toolware that is capable of solving those equations. If you have any questions, feel free to ask them in the comments down below. I will do my best to answer them. If not, thank you very much for your attention, and I'll see you next time.